Induction. Mathematical induction is a proof technique to establish a statement P of n holds true for all natural numbers. The technique requires two steps. Step 1 is establishing a base case, and step 2 is the inductive step, showing you how, if you assume that the statement is true at some integer k, that it will also be true at the next integer k. So if we verify both step 1 and step 2, we have a base case that we can start at, and by step 2, we know how to move to the next step. So if P of 1 is true and the inductive step is true, then P of 2 is going to be true, which means by the inductive step, P of 3 is true. Again, by the inductive step, P of 4 is true, and so forth. Hence, the statement will be true for all natural numbers. Nice. Let's do an example. So here's a statement, P of n. P of n is taking n copies of 2 and forming up this expression of sums and radicals. The right-hand side, we have 2 multiplying cosine of an angle. The angle is pi divided by 2 raised to the n plus 1. Good. Let's do the proof by induction, and we'll start with the base case. So P of 1, we're going to have 1 copy of 2 on the right-hand side. So that's rad 2, but rad 2 can be written out as 2 times rad 2 over 2. Rad 2 over 2 is the same thing as cosine of pi over 4, and 4 is the same thing as 2 raised to the 1 plus 1. Thus, we have a single 2 on the left, and we have 2 times cosine of pi over 2 raised to the 1 plus 1. Check mark on the base case. Good. Moving on to the inductive step. The inductive step requires that we make an assumption that P of n is true for some n equal k. Nice. So we want to go from there being k many 2's on the left equaling 2 times cosine of pi over 2 raised to the k plus 1 to there next being k plus 1 many 2's equaling 2 times cosine of pi over 2 raised to the k plus 2. Let's start with that angle, pi over 2 raised to the k plus 2. And notice that we can peel off one of the base 2's and then rewrite it as 1/2 times this angle appearing in the P of k statement. Then we can use the half angle identity for cosine, where we're going to take as our angle theta this given angle appearing in the P of k statement. So let's do that. If we start with cosine of pi over 2 to the k plus 2, rewrite it as a half angle, and then using the half angle identity, get 1 plus cosine of theta, here's our theta, all over 2. And then use our assumption, P of k being true, to swap out this cosine term. And note that it's only the cosine term. Therefore, we're going to get the radical over 2, which means that this 2 placed under the cosine term will turn into 4. I separated out that 2, dividing 1. But now I have a different denominator. So to make a common denominator, I'll multiply by 1 in the form of 2 over 2. That means when I recombine the terms, this first term will produce a 2 in the numerator. And with a common denominator of 4, I applied the radical to the denominator to get a 2 without a radical. Good. And I've kept a pink highlight to show, to keep track of. There are k many 2's here, k many 2's here. But k many 2's plus one more means that we have, in total, k plus 1 copies of 2. Good. We don't need this 2 in the denominator. We want to move it to the other side. Doing so will establish the P of k plus 1 case, which completes our proof by induction of P of n. Excellent.